Our last speaker is Alexey Dosovitsky, who has just moved from the University of Freiburg, where he was a postdoc with Thomas Brock's group, to become a researcher at Intel, founding researcher at the Intel Research Munich. Alexey is a mathematician turned applied researcher, so he's originally from Mehmet, MSU, where he has done a PhD. Then he decided to switch to computer vision and moved to Freiburg for that. He has done some seminal work, I would say, well, at least in my perspective. So our class of deep learning has his work on chair generation and generation of other stuff, and I think on a few last talks I have a slide with the chairs, of course with Alexey name on it. So it's a real pleasure to have you here, and so Alexey will be talking about several several things in one talk.
Yeah, thanks for the introduction. So, yeah, I have a long VIP slot, I think 1 hour. I'll try to finish sooner, but we'll see how it goes. Yeah, so there's quite a lot of stuff, and it's more of an overview talk, unlike others, so there will be many works, but not in much detail. Yeah, and mainly it will be about these convolutional networks, which Maxim already introduced, but I'll talk about different things, not what he talked about. And so again, the same idea, convolutional nets goes from picture to high-level implementation, and you can go also other way with this convolutional network, and yeah, what can we do with this? And what I will talk about are these things, end-to-end estimation of motion and depth, inverting convnets, actually other feature representations, inverting feature representations, and perceptual similarity metrics. And using this work, you can do some interesting visualization of neurons in convnets and some generative models. And then also, I very much hope to mention learning to play Doom, which is completely a different thing, has nothing to do with these convolutional networks, but that's what I've been doing at Intel, and I plan to do it more in the future. It's quite exciting, so I really want to mention it. Very nice. Right, so the first part is about this end-to-end motion and depth estimation, and it's joint work with a crowd of people from Freiburg and from Munich. So just in case, optical flow estimation is the task of given two frames, this wheel A and B, 2 frames, you need to estimate the motion of each pixel from the first frame to the second frame. So you need to predict a motion field at each pixel at 2-dimensional vector. And it's a hard task, so this is a frame pair from Intel. Yeah, it's kind of complicated because there's blur and there are atmospheric effects and there are large motions, and yeah, it's not as easy as one might think. What people typically do is people compute some descriptors or like just do exhaustive matching of the 2 frames and then do something global on top, like some variational method or some discrete optimization or some other kind of aggregation. And that often works well, but also it's typically very slow. And what we wanted to try is doing the whole thing end-to-end with a big convnet. So we just take 2 frames on the left and put them in this green funnel, which is a big convnet, encoder, decoder network, and just get the flow field out. And this has to do with these convolutional networks because you need to predict this whole picture, so this not just like a class or something, but the whole flow field. So you need a way to predict this large resolution image, and that's where these convolutions are useful. And so here is the actual network in more detail. This is the first version, FlowNet simple. So the input is 6 channels because it's 2 RGB images stacked, and then there are convolutional layers, and And then there's this little green funnel, which I'll explain in a moment. And this green thing takes this compressed representation, compressed feature map from the convnet and expands it to this flow field. And here is how it looks. So it consists of these up convolutional layers, and also these little gray arrows mean that the feature maps from this kind of interacting part are concatenated with these feature maps, the green feature maps in this upsampling part, so that this upsampling part via these gray arrows can reuse the features from like high resolution features from the contracting pathway. Yeah. And then there are like some intermediate flow predictions, and this is the final flow prediction, which is still not the full resolution. It could be full resolution, but we found this to be more convenient. So making it full resolution doesn't improve the numbers, but it makes things slower. There is no fundamental complication with that. It's just for technical reasons. It was easier to not go to full resolution. Right, so yeah, that's the architecture, basically convolutional encoder, and then this up convolutional decoder. And there's also another version. So the first one was really simple content, just put two frames into content and hope that it learns everything by itself. And we weren't sure that it would just work, so also designed another version, which is shown here. It's called core, and it involves this explicit correlation layer. So this starts with two parallel streams, like a Siamese network, which extracts the same kind of features from both images. And then there's this yellow little correlation thing, which takes one feature vector at one position from one of the feature maps and correlates it with all neighboring positions in the other feature maps. And then each of these neighboring positions becomes a channel in the output. So yeah, I don't want to go into too much detail, but the idea that there is some feature extraction and then there's some explicit correlation, and then there's again a usual content on top. And again, this little green thing is the same as in the previous slide. Right, and now, so we have this great nice network, but how do we train it? Of course, we would like to train it supervised, because that's the thing which really works. So mainly all successes in computer vision are supervised training, because it's like, just works. But for that we need lots of training data, and for optical flow it's hard. So for optical flow you cannot just easily just record, go out with some special camera and record data, because such a camera doesn't exist. It's really, really very expensive to get optical flow data. And yeah, so what do we do? What we did was using synthetic data, in this case the flying chairs dataset. Yeah, so we had chairs from the previous project lying around, so we decided to make use of those here to make a dataset. And it's a very simple one, so essentially we took these pictures of the chairs, renderings of these synthetic chairs, segmented them out, and overlaid them on top of some random natural images from Flickr. And the motion here is purely 2D, so, well, you don't see, but this is one of the frames, and the second frame would be with all the chairs and the background displaced in 2D, so with some affine motions. There is no 3D here, it's just purely two-dimensional motions. Yeah, and on the right are the flow fields. The color represents the direction, and the intensity represents the magnitude of the motion. So this is a very simple data set, and we weren't even sure if it makes any sense. Like, if we train on these chairs, will it really do any good? And, well, the first nice thing is that it turns out that it works on these chairs. So if we train this big convnet supervisedly on this data set, then it actually works on this data set. And it actually works pretty well, so better than state of the art at that time. So yeah, here are the two images overlaid, and here's the ground truth, and there's the prediction, the flownet core, and there's epic flow, which was kind of state of the art at that time. So on these chairs it works really well, but what's kind of remarkable is that it also works on other data. So only trained on these 2D simple motions, it then generalizes to Sintel, which is like the most common benchmark. And for optical flow, it's also a synthetic movie, but it's kind of realistic, so it's rendered in a realistic way. And again, here are the two overlaid images and ground truth and predictions of different methods. And yeah, so in this case, FlowNet does work quite okay. So it even detects some small details like the swing and this arm, which EpicFlow misses here in the bottom. In terms of numbers, it's not better because it's not very good at predicting smooth flows, but it does actually non-trivially generalize. And in terms of numbers, it's somewhat worse than EpicFlow, but it's quite okay, while being much faster. Right, but then this initial FlowNet worked quite well, but now recently there was an update to that, and I'll briefly talk about that. So one thing is that this dataset was really simple, these line shares just with 2D motions, and to address that we made U1 flying things 3D, which is very similar in spirit, but now it's actual real 3D dataset. So there it was 2D renderings moving in 2D, and here it's real rendering in Blender of actual 3D models moving in actual 3D. So like shading and lighting are realistic, and also the motions are not purely in plane, but also out of plane rotations. And it's also not just chairs, but lots of different classes from ShapeNet fly around here. So it's still not very realistic, but it's very diverse and kind of more realistic than the original flying chairs in terms of image statistics and kind of motions. And the dataset was one thing, and also we made some improvements with the architecture of the network. This is the FlowNet 2.0, the new version. So, yeah, main two ideas are stacking things and warping flow fields in between. Here is the little green thing on the left is this FlowNet core, which I described. And that predicts some flow field, and then we can use this flow field to warp the second image to the first one. So you kind of use the predicted flow to transform the second image so that the next network only has to estimate the residual flow. And this warped version of the first image and the second image and the predicted flow and the error of the first network are passed to the second one, which is FlowNet S, and then this happens again, and then there's also another branch trained specifically on small displacements, because those were a problem, but I don't want to go into much detail. And then there's a fusion. So essentially it's just a stack of several FlowNets with warping in between. And it turned out that this works really well. So this chain of dots are FlowNets. X-axis is the runtime in logarithmic scale. So lefter is faster, righter is slower, and it's in milliseconds. So 10 to the 3 is 1 second. And the y-axis is EPE, which is endpoint error. Like, less is better. And yeah, nice thing is that like different versions of FlowNet are different sizes of the network and different number of networks in the stack. And you can see that this FlowNet 2, which is like the biggest and the best performing thing, performs on par with flow fields on Sintel. It performs on par with flow fields, which is currently not anymore state-of-the-art, but used to be state-of-the-art recently. It's kind of state-of-the-art-ish. So it performs as well, but it's like 200 times faster because it's just end-to-end feed-forward estimation. There's no exhaustive matching or something involved. It's just one forward pass from network. So it's really, really fast and performs very well. And then you can also make faster versions which are not performing as well, but still performing okay. So there are some nice range of trade-offs. And one problem with the original FlowNet was that, as it turned out after publications, when some people wanted to apply it to the real data, it turned out that it doesn't work very well, or sometimes almost at all. So this is some real data set, real videos, and this second column from left is the original FlowNet. And you can see that the flow fields are very noisy, blurry, not very good. And the nice thing is that now the rightmost column is this new flow net, and it works really, really well. So it produces nice, crisp, sharp flow fields, also for very small motions, and it looks great. So there is no ground truth because it's real videos, but you can compare it to flow fields here on the left, and yeah, so it looks as well, or even sometimes better, as flow fields, while being like 2 to 3 orders of magnitude faster. So it's really, really nice. And also on Kitty, so now autonomous driving is a big deal, so everyone cares about driving scenes, and Kitty is a driver dataset. And actually, if we fine-tune this network on Kitty, that's another nice thing about this end-to-end training, is that you can easily fine-tune on your specific dataset, and that's what we did on Kitty. And here's the ground truth, and the fine-tuned flownet and other methods, and it works really, really well. And it's currently the best method which doesn't use stereo. So these icons mean that others use stereo, and we don't. We just use single images, and we're the best, while running at roughly 10 FPS, and others like take 1,000 or so times more time. Right, so it's really, really nice. And then it turned out that the same way you can do also depth estimation. So this general idea of end-to-end estimating things applies also to depth. And that's what we also did with this flying things dataset. So we trained on this flying things dataset. You have couples of frames left and right. You need to estimate the disparity between left and right in order to estimate depth. And you can also train it exactly the same way, supervised from pairs of images to disparity. And it's a simpler problem than flow because it's one-dimensional. You need just to search along the horizontal lines. And it also works really well. So the middle column is the ground truth, and the right column is the prediction of this disk net, disparity net. Also in terms of numbers, it's nice, but I don't have numbers here. Also on Kitty. And the most recent work in this line of work is this daemon, which is called abbreviation for depth and motion network. And this is also an idea we immediately had, but it turned out that it's like much harder to make it work than to think of it. And the idea is to do monocular depth estimation, not stereo camera, but just a monocular video, and train a network to estimate depth and camera motion from that. And like the hope was that you just feed the images, a pair of images. So here we just dealt with pairs of images, not long videos. The plan was just feed a pair of images there and predict the depth and motion, and it being to just work. So unfortunately it didn't just work, so this turns out to be somehow significantly harder. But yeah, so after some effort, it was possible to make also this work to some extent. So this is the overview of this thing, and I don't want to explain it at all, but it involves like several networks, some initial prediction, then some iterative refinement, and then some final refinement, and there's a prediction. And each of these things includes actually 2 encoded decoded networks, and there's some flow prediction in between and some warping, and it's kind of complicated, but in the end it works somehow. So the image on the left, ground truth, and then on the right is the daemon result compared to other. So this base O is some traditional method which people would use in some structure for motion or something. And this eigen is depth from single image. And so typically this daemon is better than both of those things. Right. Okay, so to conclude this part, you can estimate motion depth end-to-end with this up nets, and it performs state-of-the-art or close to state-of-the-art, and it's very, very fast compared to other state-of-the-art methods. Okay, so it's the end of the first part, and there are 2 more to go. How's the time? Okay, good. Okay, maybe you could quickly take questions on this part if there are any.
Maybe a couple of questions.
Okay. So for this last thing, yeah, so it was a mixture of several data sets, some indoors, outdoors, some synthetic, some real. So it was lots of stuff, and then it's like the plan is that it generalizes to any kind of data, which is not quite true, but it does generalize much better than many other things. Like much better than these single frame methods at least. I think back. Yeah.
Your data set is perfectly irrelevant or not?
Which one? This flying chairs definitely is, and flying stuff is as well. Yeah, it's all relevant. Yeah.
How do you perform mapping inside of your network, and what framework do you use?
Cafe, and it's like implemented, we implemented it ourselves, so it's just working, and you can also map propagate through it. But yeah, it was some effort to implement it.
So is it like the same as spatial transformer network, the second one?
It's kind of related. I mean, it's per pixel, so it's kind of more.
Billion assumptions.
Yeah, but it's billion. Yeah.
Do you think you do core in folder 2?
Yes. So the first one is core, and then the others are not.
Okay, because you mentioned like several on the graph, and I was wondering like the first one.
Yeah. So the first one is core, and the others are not. Yep.
So your original flow network you mentioned was a problem with the large displacements. So did you solve it eventually, or what's your issue with the model?
Well, yeah. So it's still like from the simple results page, it seems that the biggest problem currently is big displacement. So the original flownet was not very good with small displacements and with big displacements. Now small displacements are good, but big are still not perfect. I think a couple of reasons are that the receptive field, like because it's feed forward, the receptive field of the arrow has to be large enough to capture these large displacements. And another thing is the training data. So in order for it to learn these large displacements, you need to have many of them in training data. But then if you have too many of them, then you may hurt actually the small displacements. It's kind of tricky. We haven't put too much effort into it, but one might try to. I mean, the thing is that also these large displacements are not that important in real life. So it turned out that in real life, they're typically really, really tiny displacements, and that was the big problem.
Last question, please.
What about reflections and semi-transparent objects? Have you had experience with that?
Yes, so we haven't done anything explicitly about that. I guess one could, but it would require a different representation of the flow, because currently we have just regression, and if you want to have some layers.
But just to maybe show some artifacts, it's just interesting how tools like.
No, actually,
what the neural network tries to do with those things?
Well, I guess it would try to match. So if there is transparent thing, I'm not sure. No, I haven't tried. Maybe it would opt for one of the options, or maybe it would average it. No, I'm not sure. I'll try. Yeah, it's something we thought about, so it currently cannot deal with that properly, definitely. But one could try to incorporate it. Okay. Let's go on. The second part, well, maybe it will be faster. No, maybe not. So it's about inverting convnets and also other features and perceptual metrics. So I'll explain more what this means. So the first idea was on this chairs paper, which Maxim mentioned. We generated chairs from the high-level representation. So you take the high-level representation in and generate a picture out. And we're thinking, what if one takes some other representation of the image, like some arbitrary feature representation of the image, this blue box here, some features like convnet features or some hog or shift, and try to reconstruct an image from that with an convolutional network. So just train a network to take features in and reconstruct the image out. Yeah, just mainly out of curiosity, although something like this can also be useful for some image restoration tasks or so. But I mean, I personally was just curious how well it works. And it actually turns out that if you just train this, like in straightforward manner, supervised training from features to picture with usual square Euclidean loss in the pixel space, this works quite well for some simple cases. For example, here is an image, and here is a hog, like a representation of hog features, which I know, well, hopefully people know. Now it's like an old school thing, and not everyone knows that. But back in the days when I started, it was still a thing. So it's some handcrafted descriptor of the image, and it's like very normalized. So it's normalized gradients, so it isn't supposed to have any absolute brightness information in it. Oh, sorry. But it turns out that if you just train a network to reconstruct from that, then you can get a really nice picture. So this right one, it's really, really good, almost the same as the original one. And the interesting thing is that it preserves the absolute brightness in some mysterious way. But it turns out there's surprisingly much information in these 12 features. And you can also do the same for SIFT key points, so that's kind of more interesting because it's a sparse key point representation and it's a bit more tricky to make it work technically. But so here every little green point is a key point, and then you extract a descriptor at every green thing, and the set of the descriptors is the representation. And then the bottom left is the existing work who tried to invert this, and the bottom right is if you just train this big component to do this task. And it also does like remarkably well, so it nicely can kind of glue these separate key points together and reconstruct a nice coherent picture. Right, and then like somewhat more interesting thing is how much information is there in the continent features. So everyone likes continents, and analyzing them is a hard task. No one knows how to do that. And one interesting experiment is to take the AlexNet network and take features at different levels and try to reconstruct image from those. So on the left are images, and then each column is a reconstruction from a different layer. And if we also do it exactly this way, just supervised training with Euclidean laws in pixel space, it actually does work quite well for lower layer features, like it's getting blurrier, as you may see. And then even from fully connected layers, you can still kind of reconstruct the images to some extent, which is not at all obvious because you would expect that the color and the exact position and the shape may be lost in the higher layers because they're not very relevant for classification. But it turns out that even like from FC8, which is the final classification, like class probabilities layer, even from that you can somehow reconstruct the general shape and color of the image with this simple procedure. But overall it gets very blurry from at higher layers, and we would like to try to do something about that. And this was a follow-up on this work. And the problem here is apparently that the feature vector doesn't know exact details, so it's like an abstract representation, so it doesn't care about exact position of every little thing in the image. And yeah, so it doesn't know these exact details. Oh, oops. And this results in blur because the Euclidean loss in pixel space results in averaging all potential positions of little details, so you get this blurry average image as a result. And then the idea is to try to use a different loss function which would not enforce this averaging behavior, but rather would would prefer a single sharp reconstruction rather than this average blurry thing. And what we tried is this, what we call this deep perceptual similarity metric. And the idea is to compute the distances between images not in pixel space but in a feature space. So you would extract the features, in our case, some AlexNet pool 5 features, and instead of comparing the images directly, you would compare the features of these images. It's kind of related to a couple of things like this style transfer, for example. They also do it. And the hope is that these features, they don't care as much about the precise positions of things, but they care about perceptual properties of images. So like they care about sharpness and like textures, but they don't care about the texture being exactly the same as in the image, but it may be slightly shifted, like different, but the same in general. Right, so here is then the bottom left is the original image of the monkey, then the second image is this blurry reconstruction just with this pixel space loss, which I just showed earlier. And if you do this feature loss, then it doesn't get much better. You again get some weird artifacts. That's because this feature, like comparing the features of images doesn't enforce the images to be natural. So these features are like the AlexNet is contractive, not one-to-one, but contractive mapping. So the fact that the features match doesn't mean that the images match. And it turns out that there is some weird, very artifact, noisy image for which the features match very well, but the image doesn't look anything like that monkey. And to deal with that, we had a natural image prior with some adversarial training. We just like train kind of again, and I don't want to go into details, but you can enforce, in addition to this feature matching, you can also enforce the generated image to look natural with kind of again, and then it gives a nice, sharp, realistic looking monkey on the right. And then if you just do again, then it doesn't really work. So it's really a combination of this feature matching and adversarial loss what works best. And okay, so here again is the Euclidean loss, blurry stuff on the right. And then with this Euro loss, you can get really nice, sharp reconstructions also from very high layers. And I will go back and forth a couple of times. Yeah, so even from lower layers it gets nicer and sharper, but also from higher fully connected layers it gets much better with this loss. Again, like the images can be reconstructed remarkably well, even from the predicted class probabilities. And here are some more results on that. So it's the images and then the constructions from conv5 and fully connected layers of AlexNet. Right, so surprisingly much information is preserved in the higher layers of convs. And then this loss, like I was mainly interested in this CNN analysis, which is kind of useless currently a little bit, but one can also use it for some practical image generation tasks like super resolution. People have done it, and so the image compression, denoising, and the kind of image processing one could do with this exact loss. And then what we actually did do with collaboration, in collaboration with some people from Wyoming, is applying this to analysis of deep networks and to generative models of images. That's what I'll talk about next quickly. Yeah, so visualizing neurons and generating images with Hank, Jason, and Jeff from Wyoming. Right, so what these people have been doing for a long time is called activation maximization, which is you take a convnet and then you select a neuron, some like output neuron of this network corresponding to some class. In this case, I guess some deer or something. And then you run gradient descent through the network, and you optimize the input image in such a way that the activation of this selected neuron is maximized. So you try to generate an image which maximally activates a certain neuron. And the hope is that if you select a deer neuron, then by generating this image which maximally activates the deer neuron, you would like to see a picture of a deer. But the problem is that as I said, many different images correspond to the same features or correspond to the same activation. So what you do if you just do this optimization is what you get is just some noise, as here in the top right, just some meaningless noise. And in order to get something reasonable, you need to introduce a prior on the image to force it to be a natural image. And all the different pictures shown here are these results with different hand-designed priors. Like they usually do some TV and some L2 regularization, and by tweaking the parameters, you can get like different images, and in some of them you can see some. Well, you should be able to see some deerness, like some horns and so on. So you can kind of see something when you do this, but it's not great. And what we did was using this upconvnet from the previous part, so this upconvnet was trained to reconstruct images from FC6. We use that as prior, and okay, I feel like I don't have much time, but maybe let me try. So here's on the right, the green thing is the image, then on the right of the green thing is the convnet you want to visualize, AlexNet, and on the left of the green thing is this up convnet which was trained to reconstruct images from FC6 features. And all the networks are fixed, so there is no training happening, the networks are fixed, pre-trained. And then you take a neuron in this network of interest, like Candle in this case, and then what you would do in this activation maximization I just described, you would just backpropagate to the image and optimize in the image space with some regularizer. And what we do here is we backpropagate all the way to the image and then to the code space, and we optimize directly in the code space. And the idea is that then the image is generated by this upconvnet, and this upconvnet only can generate reasonable images, so this upconvnet acts as a prior. And we optimize in the code space instead of the image space. I hope it's reasonably clear. doesn't really matter, but this upcomponent, this pre-trained upcomponent acts as a natural image prior. And the cool thing is that with that you get really nice pictures. So these are the results of this procedure for different FC8 neurons, so for different classes. You select a class and then you generate an image which maximizes the activation of this class, and then you get all these nice pictures. And like the good thing is that the pictures and the names correspond. So you start with the class name and then you generate the picture, and nicely the picture actually looks like something from this class. It's kind of non-trivial, it hasn't happened before. Right, and it also works for classes from other datasets, from places datasets. So one might think that the network kind of overfitted to ImageNet and just remembers the whole ImageNet, but you can also do it on another dataset and it still works nicely for these places. And another fun thing you can do with it is you can not activate a single neuron, but activate 2 neurons. So here are still single neuron activations, some classes, and then you can add candle to all of them, and then like this magic happens. You can like get all this piano in flames is very nice, and also these lobsters are very nice. So I like the lobsters. Here they are in the sea, and then they are on the plate in the restaurant. That's great. So yeah, nice art with comments. And you can also do it for intermediate layers, and you can try to visualize what the network learns in the intermediate layers. It's not always interpretable, but sometimes it is. So you can do activation implementation for any neuron in the network and try to see what it likes most. Right. And then, so this was nice, nice result. It generates good pictures from convolutional, but it's not a real generative model yet because it just generates these images which maximally activate the neurons, but it cannot generate very diverse images. So there is some diversity, but not much. And turns out it's not very hard to turn it into a generative model, and that's like a recent CPR submission. Okay, let me really quickly do it. We call it plug-and-play generative models because we can just take any classification network. So it's kind of similar in spirit to this activation optimization I just described. And in the same way, you can take any network and then run this plug-and-play thing for this any network and generate images corresponding to this network. I guess it will get clearer in a moment. So for example, here on top are top 9 images from some class, some flower cardoon, I think it's called. And here are top 9 images, and here are random 9 images. And this activation optimization I just described, it generates something similar to this top 9 images because it's trained to maximize the activation, so it generates the most kind of stereotypical representatives of the class. But what would be nice to have, like a proper generative model, would rather generate the whole diversity of the images. And this plug-and-play generative networks does more or less exactly that. So it's this bottom right result. It turns out that if you just do this activation optimization but also add some noise in the process, then it can be shown that this corresponds to some MCMC sampling, and it becomes kind of a proper generative model and generates diverse images now. And for some classes especially, it looks really great. Like these birds and ants and palm tree and volcanoes are especially nice. It's still not perfect, and for some other classes it doesn't work that well. But it's still very impressive that with this simple procedure, just by adding noise, you get very nice, high quality, high resolution images. More or less state-of-the-art quality. And this nice plug-and-play property allows you to take any other model. For example, you can take a network trained for image captioning, which converts images to sentences. And then you can do this process with this network. And this allows you to generate pictures conditioned on sentences, something which others also have been doing. So you can take a sentence and then try to generate an image which kind of activates this sentence. And then you can get results like this. They are like not perfect, but quite okay. And you can see that it really cares about the content. So here it says a red car parked on the side of the road and generates something like a red car, and a blue car generates a blue car, and then pizza on a plate. pizza just about to be cut, and then some oranges, and then more oranges. It really, yeah, that's something reasonable. Not perfect, but nice. And it's cool that you can just take any recognition network and then do this process and generate corresponding images. Right, this concludes this part of the talk. So perceptual networks are great, and you should rather use them than Euclidean laws. Convnets can be inverted very well, and these plug-and-play generative networks can generate very nice high-resolution images. Yes?
Should we do something similar to music? It's like inverse.
Well, you probably could try. Yeah, we haven't, I guess. I mean, in principle, I'm not sure how well it would work, but yeah, it would be interesting to try.
High resolution images, how high is resolution?
227 by 227. It's like, typically it's 32 by 32 or 64 by 64, or recently sometimes 128 by 128, so this is like by standards of generative models, it's high.
By perceptual metric, you mean like the difference between activations in the different network?
Yeah, well, I mean, we call the whole thing perceptual metric, but yeah, I mean, this difference between acceleration is probably crucial. Well, I mean, also the adversarial part is crucial.
Perceptual is a combination of the two.
Yeah, well, that's how we called it, but I think other people have called it in other ways. Yeah, so there may be some confusion.
Yeah, and the performance of the like the quality of the resulting images seems to depend much on the adversarial component, yes, as you show.
Yes.
In addition to the perceptual feature. And adversarial networks, they are known to be hard to control so that they don't diverge to like trivial solutions. Could you share some secret recipes how to like tame them?
Well, there was a recent tutorial, I think at NIPS by Sunith Chintula, and I think it's great, and you probably should check that out. I'm not such a huge expert on GANs. I think Sunith is a better guy, so I would say just that in this case it was not so hard because it was not the only component, so there also were these other losses and they kind of made everything more stable. So I think it's harder when you just have a GAN, and here you have also other things and it kind of gets more stable here.
So you compensated and it didn't require additional tinkering with the...
Well, it still was kind of not trivial, but I think it was easier than in other cases because you also have other losses to make things more stable.
Thank you.
And how you
And
compare?
Canada, that is like following this NIPS workshop, they established a GitHub web page where list all the tricks and some
Yeah, but maybe there are some specific to this work.
No,
Thank you.
really.
And in which combination do you combine these perceptual loss from which activations, which is space activations, and them? So
It's
like
like some.
50 or...
Oh, well, there's some waiting. You can check the paper and there is no code online. But so this feature is like a major part of the loss. The weighted feature loss is roughly 10 times or something higher than the weighted GAN loss. Yeah.
But you told that if you combine GAN with a loss in RG space, it will not work. But if you use BGG features, it will. So what is the implication?
Well, in this case, it's kind of a very hard task to reconstruct image from its features, and GAN will also kind of just learn to do it. Because in order to do it, the GAN will have to learn to extract the features from your image and ensure that they match the original features, and that's kind of hard. And this perceptual method, it explicitly matches actually the input image to the output image, so it provides much tighter supervision somehow, so it's easier to learn. And again, GAN kind of has to learn to do it from scratch, and it cannot.
It's more responsible for the sharpness of the image, yeah.
Yes. Well, it's responsible for the naturalness of the image, but it's very hard for it to actually learn to produce the matching features.
But if I understood correctly, you tell that if you use RGB and GAN, it will be better than, it will be worse than using VGG features and GAN. So
yes.
in both cases you have supervision beside GAN.
Yeah, but RGB is bad supervision because it leads to all this blurriness. So if you have RGB and GAN, then you kind of get this blurry image, and then GAN ensures that it's not blurry, but it kind of looks sharp, but it doesn't ensure that it actually matches the original image. And generate something which is kind of sharp, but not necessarily matching the input image. And then the feature loss actually ensures that it actually matches the correct image. Okay. How much time do you have?
20 minutes.
Ah, nice. Quite on time. Okay, well, I may even finish earlier. Oh, oops, London disappeared. Okay, yeah, so this is now a completely different topic, playing Doom, kind of reinforcement learning kind of thing. And that's something I did at Intel, and it's like there's a mission, and it's with Vladimir Colton, who somehow disappeared, his picture. Anyway. Right, so motivation for this work was that like traditional mainstream reinforcement learning people do recently is kind of restricted. So you typically have a single goal, like in some Atari game, for example, you need to win the game, that's your goal. Okay, as opposed to real life, where you have a number of different goals, like a real human doesn't have a single goal to achieve, or like some robots ideally wouldn't have a single goal, but would have multiple different things it can do, and you would want your agent to be able to do different things, not just one. Then related to that, the only training signal the agent gets is the scalar reward, so there's some reward signal which tells the agent if it's successful or not at reaching this goal. So if it's doing the right thing, then it gets like some positive reward, some cookies, and if it doesn't do well, then it gets negative reward, eating. And yeah, so this scalar reward is the training signal for the agent to learn to do the right thing. Well, in real life, it's not like that. It's not like humans, animals, robots, autonomous cars. They don't just get a single number. They get lots of stuff. So they see the world, they hear things, they like touch things. They also like feel different things, hunger, pain, and so on. It's not just scalar reward. It's a rich sensory stream. And then following this line, the way the training works in most traditional RL scenarios is that you maximize this expected returns, which is a discounted sum of the future rewards. So you want to maximize the amount of reward you get in the future. And what one might want to do is not just do that, but also like explore the world, learn about the world, and like see how the world works. And yeah, so we wanted to try to do something which is more like the right side of the picture than the left side. And what exactly we did is this. So we want to predict, instead of maximizing the reward, we want to predict future measurements. We call them measurements. And these are some meaningful values the agent perceives from the world. And these values are expected to be important for the agent's behavior. So for example, for an animal, it could be a sense of hunger, pain, coldness, and sleepiness. And for a Doom playing agent, because we actually do it in Doom, these measurements might be health, ammo, and frags. And these are natural things which are naturally available to the agent, so it's not really hacking, so it's not something agent normally wouldn't know. It's something it does know, like a human. When a human plays Doom, human does know health, ammo, and frags. So it's okay. We don't feel bad about using these things. As some orthodox RL people might. And yeah, and it makes sense that these things would help learning something interesting and useful about the world. And so what we want to do is we want to predict these measurements in the future and use that to behave. And the key assumption is that the goals of the agent, so the things the agent may want to reach, can be formulated in terms of these measurements. So we assume that like everything an agent may want to do is maybe like minimize this hunger and pain, coldness, sleepiness, or maybe like minimize some weighted sum of these. If the agent is very hungry, for example, it may want to prioritize minimizing the hunger and not so much the other things, and so on. And this Doom agent may typically want to maximize health and run threats in some combination, like depending on the circumstances, or maybe the weighted average of these. So this formulation seems to be reasonable and seems to include a good range of realistic scenarios. It's probably not the end of the story, it's not the ultimate thing, but it is meaningful and more general than the standard RL formulation. And what we do is we just predict these future measurements with supervised training. So that's another idea that we know supervised training works very well, so we just want to try to use that. So just the agent acts in the world and things happen, and then you can use the future events as supervision for the current time step. So we just wait for some time, see what happens, see what are the values of these measurements in the future, and just train in a supervised way to predict these future measurements from the current state, which is the picture the agent sees, and the current measurements, and also the next action to be taken. And again, it's very brief, so yeah, if you don't get it, have a look at the paper or ask me. And this is, again, very quickly the actual network we used to do that. So not surprisingly, it's a big convnet, and it takes the image, the current measurements, and the goal vector, which is a very interesting thing about it. Again, very quickly, it needs the goal vector because, all right, so first the goal vector is are the weights for weighting these future measurements to form the objective of the agent. So as I said, objective of the agent is a combination of these future measurements, and this goal vector are the actual weights in the linear combination of these future measurements, which actually define the objective. So this goal defines the actual thing the agent currently wants to do. And this future predictor actually needs to get this goal as input because the future will depend on the goal of the agent. It's well, for example, if the agent wants to maximize the health, then you would expect the health to go up, and if the agent suddenly wants to commit suicide, you would expect the health to go down. So it's very important to make this future prediction conditional on the goal. And then they are processed by some convnets, fully connected, whatever, and then there is the actual future prediction conditioned on the current action. So I guess there is no way to really understand it now, but essentially it's just simple supervised training, predicting future measurements conditioned on the next action. And we evaluated in this least Doom environment, which is based on Doom, and we had 4 scenarios. Basic, it's a square room with some health kits, then I will show a video in a moment that will be probably clearer. The second one, which is again collecting these health kits, but in a labyrinth, and also with some blue bottles which are acid, so it should avoid the blue things and collect the green things. And then 2 scenarios involving alien monsters, like a simpler one and some simpler labyrinth, and then this D4 in a more complicated labyrinth with like some stairs and mirrors and objects. So these are gradually increasingly difficult tasks. And here are the results. So higher is always better, and the 4 plots are the 4 tasks, and the red thing is our thing, green is A3C, which is some kind of state-of-the-art reinforcement learning algorithm, and blue is DQN, which is the Atari playing thing, and the little purple thing is something else which doesn't really matter. It doesn't really work very well. And you can see that on the simplest scenario, everything works more or less, and then on the harder one, our thing always gets a little bit better than A3C, apparently. And then on the 2 hardest ones, our method actually works much, much better than A3C, which is kind of remarkable. So it essentially works, while A3C essentially doesn't quite work. And here's a video. Hope it plays. No, it doesn't. Not yet. Oh, actually, press it maybe. if there is some time. Oh, no. Just okay, yes, so it shows these 4 scenarios, and for each scenarios, 3 methods, DQN, A3C, and then our method. So in the simplest one, everything works, okay.
So this is some simulation of some level, yeah?
Well, yeah, I mean, it's like, it's some environment.
Okay,
so it's not the actual game.
I mean, it's a specially prepared level.
Yeah, so it's a special scenario design there, yeah. It's, well, I mean, it probably could play actual Doom to some extent, but not very great. So it's not close to humans yet. It can do something like better than some DC methods, but there is still a long way to go. Yeah, and then, so this is more interesting. This involves shooting, and here TQN fails completely, more or less. I mean, sometimes randomly, yeah, like if it's really lucky, then it does shoot someone. And A3C is somewhat better, but also not very great. And then our method is really awesome. Yeah, so it just runs around and kills everything. Oh, which it was trained. Well, not everything, just the alien monsters. Just the evil alien monsters. And it's actually defending against them.
Right.
Yeah, and then it's this harder one, the killer is really, really, really sad. And then A3C does something, but it just stands still and occasionally shoots a monster if the monster approaches. And then our thing is also not perfect, but it does do meaningful things. So it runs around and actually tries to somehow avoid the incoming fireballs, not always successfully, and yeah, does much better. Good, yeah, and then also a version of this thing trained with some random textures. We submitted to this Wisdom competition, which is a competition where different AIs compete in previously unseen Doom maps. So we needed it to generalize to new environments, and for that reason we trained it with random textures, and then it generalized quite well, and we actually won that nicely, as shown here, by quite a large margin. Right, and that's more or less it. So now a very quick outlook. So one thing I was talking about is this motion and depth estimation, and that used synthetic data. Also things Maxime talked about used synthetic data, and that's I think in general an interesting topic and direction, combining deep learning with simulation, because deep learning needs lots of data and simulation can provide that. And that's also related to transfer learning. Alina was talking about, and others. Then there is a connection between these generative things and control. So one very important application of the generative models could be learning models, generative models of environments, which can be used in different ways. For example, predicting the future. It's what some people are trying to do, but not very successfully so far. One could do planning. If one could learn a very nice model of the environment, then one could plan ahead what to do in the future. This currently doesn't really work. And one could do analysis by synthesis if one had a very good generative model. There's also this nice connection between perception and control. So here, people are mainly doing computer vision, I assume. And the typical scenario would be that you first do vision and then apply it to control. But now it gets more and more apparent, and like many people work in this direction now, that it makes sense to do both things jointly. So it makes sense to not first solve vision and then move to control, but it makes sense to do perception and control jointly, maybe end to end or like simultaneously in some way. And the idea is that well, again, it's just like 3 minutes. Yeah, thanks. Right, and if you do both things jointly, then also the perception side can benefit from control. So it can be useful for your agent acting in the environment. It can be useful for it to go around and potentially touch things and learn from the combination of different modalities, not just do perception separately. Right, and that's it. Yeah, so I talked about these 4 things, I guess. Yes, right. And thanks for your attention.
So in the third experiment, when we were shooting monsters, I noticed that your agent was actually shooting where there was not yet something there. You
Well,
couldn't really see it.
yeah, I think it kind of wastes ammo a bit because there's quite a lot of ammo and it kind of doesn't care too much about sometimes shooting just in the air.
But is it happening that the monsters are actually not there, but it somehow knows how they, how they move?
No, I doubt
Maybe
it
there
can
are some
happen.
pixels of monster there, but you don't see them.
Well, yeah, I mean, it might be, but it seems to generalize pretty well. I mean, this competition, for example, it definitely hasn't seen it before, so it was on the maps which were held out, so it does definitely generalize quite well. I don't know, I mean, one might try to really carefully investigate it, but I doubt that in this case it happens. I doubt it. Like, I mean, there is definitely some randomization. It might be that there is some random seed and it learns to exploit that, but I don't think so, honestly.
What's your take? So, like multi-agent systems, for example, if you were not just a single shooter in Doom, but 2 of them or like a team, could you learn not to shoot each other? Could you learn to like cooperate, exchange weapons?
Yeah, of course. In principle, I mean, it's hard, but I think there was 1 or several papers at NIPS about that. Yeah, so people are working on it. It's kind of not trivial, but can be done.
Can I ask a mean question?
Oh.
So, well, classical Doom had some AI which was very customized for a particular game and played much better, right? That all methods who don't think about Doom when they begin to learn. So isn't telling your agent about such things as ammo, health, etc. just a step in that direction, using a very customized agent, which is sort of brings the improvement?
Yeah. Well, to some extent, and I mean, yeah, as I said, I don't think it's a bad thing because I would say that it is something which is naturally available to the agent. It's not like getting hackily extra information from the engine, so why not use it? Also, like a real robot or a real car will have some extra information. I think it's okay. But also, it seems that even just with a single reward, our thing in this scenario worked kind of somewhat better than RL methods, but it may be specific to this setup. So of course it gets more information, and of course it's a large part of why it performs better, but that's also largely the message of our paper that if it's there, then why not use it?
So maybe you can elaborate on that additional bits of information in the other models in A3C and ATN, were they like given to the models or in form of a reward or as input, or they were completely ignored by the others?
Well, the reward was kind of, so the goal was the same for the ATN and A3C and our method, so it was a linear combination of ammo, health, and kills.
Yeah, so at least in
so
the
it
reward
did
they
kind
were
of
low.
implicitly included, but it didn't get this explicit decomposition. So kind of the reward was a combination of this, but not the explicit separate parts. And it's an interesting experiment to actually, like take A3C and let it also predict these things and see how well that works, and we actually want to do that at some point, but haven't done it yet. But that's also something, like, there are some IClear submissions from DeepMind which kind of go in this direction.
When your paper will be available?
It is, it's an archive. And, yeah.
Do your experiments actually show that a run does not work, and it's better to convert it to supervised training if possible, to do whatever to get supervised training?
Well, I mean, to some extent, so you probably need to cleverly combine both. So probably just pure RL just with a single reward is not the very right thing to do. It's kind of interesting theoretically, but it's not, I mean, it's overcomplicating the problem. Probably also does just purely supervised learning won't work in many cases, because like, I mean, you will probably never get better than your teacher, and like, you need lots of training data and so on. But probably a clever combination of both would be the best.
So your network takes the immediate action as an input that predicts a sequence of future actions, right?
No, it predicts the future measurements conditioned on the next action. And then it selects the next action based on this. So like at test time, it predicts the future measurements for all possible actions. So there's just a discrete set of actions, and it predicts the future measurements for all possible actions it can take, and it selects the action based on its objective. So
it predicts one action, only one action.
It predicts further in the future, but it's conditioned only on the current action. So kind of, if I do this now, then after some time, what?
But then you do exploration, so it's not very supervised.
Well, it's this supervised, it's on policy, but I guess we can discuss offline.
How does the goal, the weights and the goal, how do they change in the test time?
Yeah, so I didn't talk about that. So one option is just to have them fixed, and that's what we did for this comparison to other methods. But you also can, during training, randomly sample them, and then during test you can select anything you want, and it kind of does work. So if you train, even if you train with a single fixed goal, like to shoot everyone, then at test time you can still change this goal, and it works somehow magically. So you can like tell it not shoot anyone, and it doesn't shoot anyone. But what you also can do is you can train with just random goals, and then at test time select any goal you want, and that kind of works as well.
Okay, thanks a lot for such a plentiful talk.